There are a lot of terms that describe light. Light, of course, is the one that we most commonly use, but there are two other primary terms that we use to describe light. They are radiation and electromagnetic wave. Now, radiation is commonly known in the public as the hazardous material left by nuclear waste. That is not at all what radiation really is. Radiation and electromagnetic wave are exactly the same thing, and light is one type of radiation. So these are all really the same thing. But what is light? What is an electromagnetic wave or radiation? Really, light is nothing more than oscillating electric and magnetic fields. And as these electric and magnetic fields oscillate, they propagate through space. Now, electric fields will propagate one direction, but magnetic fields will propagate perpendicular to the electric fields. So in this figure, you see the electric fields oscillating up and down, but simultaneously the magnetic fields are oscillating into and out of the screen that you see right now. And this whole time that they are oscillating perpendicular to each other, they are moving to the right, a direction perpendicular to both the electric and magnetic fields. Now, the properties of radiation or electromagnetic waves are determined by the wavelength of the wave itself. By the wavelength, we mean the distance from the crest to the next crest of a wave. And so when you see a peak in the electric field, the next time you see a peak, the distance between those two peaks, that is your wavelength. And it is this wavelength that determines the properties of a particular type of radiation. So we just described what light is physically, but now let's talk a little bit more about it mathematically. Here's an equation that relates three important variables of light. One is the speed of light, which is actually a constant number and doesn't change. The other two are frequency and wavelength. We already defined wavelength to be the distance from one peak to the next. Frequency would be the number of peaks that passes by in a certain period of time. For instance, you sit at the beach and you watch and you see 10 waves roll into the beach in 1 minute. So the frequency would be 10 waves per minute. Now, light waves happen much faster than ocean waves, and so we don't count the number of waves per minute, but the number of waves per second. So if we saw 70 waves come in every second, it would be 70 waves per second. Another way to say waves per second is hertz. So 70 hertz. The exact same unit that you have, say, on your FM radio in your car. You turn to 103.3 megahertz, and that is what frequency is. Now, the speed of light is a constant. It is a number that will never change. Speed of light is 300 million meters every second. That is how fast light travels in space. The speed of light is the product of the frequency and the wavelength. So since the speed of light is a constant, then the frequency and the wavelength are inversely proportional, meaning if you have high wavelengths, really long waves, they will occur less frequently. Okay, with the definitions of wavelength and frequency, we're ready to talk about the electromagnetic spectrum. The electromagnetic spectrum is just a chart that shows the different types of radiation you can have based on the wavelength and frequency of a particular electromagnetic wave. In the top region here, you see we have long waves and short waves. These long waves and short waves, the wavelength is larger than anything else than the rest of this chart. So you have high wavelength. As a result, you're going to have low frequency on the order of 10,000, 100,000 hertz. Now, this long wave and short wave region, this is where we would often find most of our radio waves, say communications, AM radio, FM radio, satellite radio, even cell phones work in the long wave and short wave range. You also have, when we get to slightly shorter wavelengths, we have microwaves. In this range, we have television that works in the microwave region, weather radars work in microwaves, as well as the simple appliance that you have on your counter to heat your food. They literally emit microwaves to warm up your food. Yes, microwaves are a type of radiation, but it does not make your food radioactive. It's heating your food no different than sitting on the beach warming up from ultraviolet rays, which you see farther down the list here. Before we get to ultraviolet, though, let's talk a little bit more. Infrared. Infrared is the type of radiation that gets really close to the visible spectrum, but our eyes still cannot detect it. However, we do have to deal with it all the time. Our bodies, our Earth, the planet, everything around us emits infrared radiation. In fact, we have satellites up orbiting the Earth that take pictures of the Earth in infrared so that we can see, even on the dark side of the Earth, we can see what's happening. I mentioned earlier ultraviolet light. These are really short wavelengths. This is the type of radiation that's just beyond the violet region of the electromagnetic spectrum. Our eyes cannot see it, but we can definitely sense it. As I was talking about earlier, you go out onto the beach, you sit out, you just let the sun soak you. You feel warm because you are absorbing ultraviolet light. Right in between infrared light and visible light is this, did I say invisible light? Between infrared light and ultraviolet light is visible light. This is the region that our eyes are accustomed to seeing. And we can distinguish between specific wavelengths of visible light. These specific wavelengths are what determine the color of light. These smaller frequencies, so higher wavelengths, would correspond with red colors, and the higher frequencies, or smaller wavelengths, indicate violet light. Beyond ultraviolet light, you have X-rays, which are what dentists use, and as well as other medical practitioners who take X-ray images of your body. And beyond that, we have gamma rays. This is where we have to worry about radioactive material. Gamma rays are very high in energy and so can have an effect on our body. Whenever people say radiation, this is what they think of are gamma rays. Really, radiation is this whole chart. Okay, enough on that. Let's talk a little bit more about light. There are two interesting ways to look at light, and these two different ways both describe light very well. An interesting thing about light is that it behaves like a particle flying through space, but at the same time, it acts like a wave or a ripple going through space. It acts like both of these principles at the same time. So we have two different ways of looking at light. We have the light ray model, which is treating light as if it's a particle or a photon that travels in a straight line. When we do this, we usually illustrate the path of light using a ray, just an arrow. We use this with mirrors, with prisms, lenses, anytime we have to deal with reflection and refraction. The wave model traces motions of the wavefronts of light. This will explain interference patterns, diffraction patterns, polarization, stuff that we will talk about this chapter. The interaction of light with matter will depend on a number of things: the smoothness of a surface, the nature of the material, and the angle at which light hits the object. There are three different things that can happen. One, light can come and hit the surface and be absorbed, and then that's the end of that photon, it's gone. Another option is it could be transmitted, so absorption and transmission are related. It can be reflected, in other words, the light comes in and then just bounces off that surface, or it can be refracted, and by refracted we mean it enters into the surface but at a different angle. And all of these we'll cover a little bit more through the chapter.